let us look at the seawater pH measurements. So before 1989, seawater pH was typically measured using glass electrode with uncertainties as much as 0.1 unit. Now we had seen that what is the great amount of change of hydrogen ion concentration if there is a difference of 0.1. So if the experimental error itself is 0.1 unit, then it is actually going to create lots of problem in our entire understanding and analysis. So back then people don't even know what was the temperature at which it was measured, because we know pH actually depends on temperature and pressure. The 1980s spectrometric, that is the dye solutions, were used for the pH measurement. So that is the second method. So either glass electrode can be used or the dye method can be used. These are all the common method by which pH can be measured. Millero and Perez table can be used for calculating the seawater pH as a function of temperature, salinity and the concentration of dissolved CO2. So this table is one better method of understanding what is the seawater pH measurement. Another one is Tsuruhashi's table. So using this table, we can also use the 3 carbonic acid substances that we have seen earlier, based on water temperature, pH level and chlorinity. So carbon dioxide is very crucial for change of seawater pH, and that also leads to ocean acidification. So all these things are interrelated. So that's the reason when we look at studying about or measuring these things, we are using many of the similar compounds. Another one is gridded partial pressure of carbon dioxide and total alkalinity estimated from gridded sea surface salinity and nitrate. So this is also another method by which we can actually measure the seawater pH. Then glass electrode pH meters, which is a traditional method which many people have been using. Colorimetric method can be used using the dyes. Spectrophotometric method, microelectrode method, potentiometric methods with pH sensor, titration method, ion selective electrode methods are some of the methods currently people are using. So another major thing, the difference what we actually see is the pH change between regions. Actually, even though we say the ocean pH is X or Y, it actually changes from region to region. So when the initial pH values between two sites differ, the trend in hydrogen ion concentration also differs. This we already know. When the change in the pH is actually identical, then what we can say is the ratio between the two trends of hydrogen ion concentration equal to the ratio of the two initial hydrogen ion concentration values. So that also remains the same, that we can actually say. So if you are going to compare between two regions, then we also need to know what is the starting pH at both the places, and then what is the change that is happening in the both the different places. And ideally, peak-to-peak amplitude of pH variation at location having different annual mean pH implies different peak-to-peak amplitude of H plus ion concentration. So this is another thing we have to keep in mind. Some studies have actually reported it is expected that the seasonal amplitude of pH that is expected to decrease, while that of the hydrogen ion concentration alone. See, amplitude of pH may change, but the hydrogen ion concentration is expected to increase on the surface of the ocean. So this is what, because why H plus ions are increasing? When the CO2 gets dissolved, so what actually happens? Carbonic acid is formed. So when the carbonic acid forms, what happens? It undergoes dissociation. So during the dissociation process, it releases in the first stage. When it forms the bicarbonate anion, it gives 1 H plus ion. When it gives the carbonate anion, it gives 2 H plus ions. So in other words, what happens is the H plus ions amount increases. In other words, the concentration of H plus ions increases. So that is what it is given. So these H plus ions may reach the surface of the ocean. Compared to open ocean, the pH change occurring in the coastal water tend to be larger. Why in the coastal region that problem is actually more, the pH hydrogen ion concentration is more, is because there are various biological activities are happening and ice is also melting, which is also bringing lots of ions, and also upwelling is also another reason. So these are all the reason the coastal region has a higher H plus ion concentration, or the pH occurring at a higher level. And due to the large vertical gradients in the background pH, it is very difficult to predict the absolute chemical change by focusing only on pH. Say for example, I want to understand what is actually happening in this particular region. Let us say Arctic region I am going to study about. So it's very difficult to exactly say what are all the chemical changes that are happening just by looking at the pH. So just by relying on pH alone, we cannot predict many of the chemical changes that are happening in the ocean. So here is a Jerome plot which talks about changes in carbonate species concentration with changes in the seawater pH. So that means if the pH of the ocean is in the higher pH, alkaline region, or it is in the neutral region, or it in the acidic region. So between these regions, what is the important species that will exist? The carbonic acid, we have three species. One is carbonic acid, neutral one, bicarbonate anion, and another one is carbonate anion. So between these three things, which one will exist at what pH? So that is what this plot actually talks about. So carbonic acid is actually there, and if you look here, CO2 is at this pH. So here is the pH scale from 2 to 10. So this is the acidic region. So in the acidic region, let us say up to 6 pH. Basically, in this region, we have the carbon dioxide concentration, that is just carbonic acid that exists. And then in this region, from 3 to up to 12, in this region, in the red line, what we are seeing is basically the bicarbonate anion. So the bicarbonate anion increases from the 6 pH to up to 9.2 pH. The concentration of bicarbonate anion is the maximum one. Up to pH 6, the carbon dioxide or the carbonic acid is the major species that will exist. And beyond 9.2 pH, it is the carbonate anion that exists as the major species. So that's what the green line it talks about. So what we can say is the amount of a carbonate anion is maximum when the pH is beyond 9.2 or 9.3 pH. So by this we can say what is the pH range. Based on that we can identify which species exist in the maximum concentration. So what is the relationship between the carbonate system and the pH? That's what we had seen. So the relative concentration of carbonate system species as well as the pH in seawater are related to the following conditional equilibrium constants. So we have three species, H2CO3, HCO3 minus and CO3 minus. All the three species are existing at a different pH. So the K1 prime and the K2 prime are coupled with the definition. So here we are given. So this is the first equilibrium. This is the second equilibrium. So you already know how to write the equilibrium constant. So we take the product of the concentration of the product by the starting material. So that is the standard method of writing a equilibrium constant. So here in this particular first stage of the reaction, carbonic acid is the starting material. H plus ion and bicarbonate is the product. So H plus ion and HCO3 minus ions are in the numerator and the concentration of H2CO3 is given in the denominator for the first equilibrium constant measurement. And when we go to the second equation, this bicarbonate anion is considered as the starting material. So that is getting converted to H plus ion and CO3 2 minus ion. So of course in the overall reaction we wrote 2 H plus ion because we included this hydrogen ion also in the equation. But when we are writing the equilibrium constant, it is only the bicarbonate that is getting converted to H plus ion and carbonate anion. So here when we measure directly, we can measure the pH. And the total alkalinity can also be measured. From that we can actually, using this particular equation, we can calculate what is the pH. So similarly, the total inorganic carbon concentration and CO2 fugacity are closely, which is nothing but partial pressure. We can also call this as a partial pressure. PCO2, some people write that. K prime naught is represent the CO2 solubility in seawater. So with that we can actually identify when we talk about the total alkalinity, which includes bicarbonate, carbonate, boric acid, hydroxide anions and H plus ion. All these ions are included when we calculate the total alkalinity of that particular water. And when we talk about the total inorganic ion concentration, we mainly focus on carbonic acid, carbonate, bicarbonate anion and carbonate anion. Oh, these are all the three species which contains carbon. Here we also have boric acid, which does not have carbon. Hydroxide anion does not have, and similarly H plus ion also does not have carbon. So that is why this is called as a total alkalinity, and this is called the total inorganic carbon contents. And this fugacity or the partial pressure, when we talk about, this is the concentration of bicarbonate carbonic acid divided by the first equilibrium constant, which is where the CO2 solubility in seawater. So let us look at the carbon in chemistry, the chemical reactions that are happening in and talk about the sea alkalinity. Here we assume the temperature is 20 degrees centigrade, salinity is 35 and the pressure is 0 dbar. And here we have atmospheric carbon dioxide. The atmospheric carbon dioxide gets into water. So when it enters the water, it becomes CO2 aqueous, and that CO2 aqueous reacts with water to give H2CO3, which is the carbonic acid. The carbonic acid then gets dissociated into bicarbonate anion and H plus ions, and then this also undergoes dissociation into carbonate 2 minus anion and H plus ion. So when we talk about alkalinity, we are actually talking about the concentration of all the other ions. Bicarbonate ions are there, carbonate anions are there, phosphates, hydroxides, H plus ions, borates, sulfates, persulfates and silicates. All the types of ions which are present is actually considered. Let us look at, we talked about the temperature, how it affects the pH. So we will be focusing mainly on the sea surface temperature and the pH. So here one important thing what we have to know is the calcium carbonate mineral saturation state and pH are two important matrices for our ocean acidification. So carbonate is nothing but, this calcium carbonate is nothing but the carbon dioxide gets into water, converted to carbonate anion, which reacts with the Ca2 plus ion to form the calcium carbonate. So this is how the CO2 is basically converted to calcium carbonate. So that is component number 1, and then pH is the second one. So these are all the two important parameters when we talk about ocean acidification. And there are three biogenic carbonates are aragonite, calcite and magnesian calcite. So we will talk about this in the next module elaborately. Surface ocean aragonite saturation state shows a large latitudinal gradient and is strongly associated with the sea surface temperature. That means aragonite saturation state is related to sea surface temperature. And the surface ocean temperature measured at 2000 shows a small latitudinal gradient and is weakly correlated with the sea surface temperature. See, the temperature controls the surface ocean pH and the saturation state of calcium carbonate. We will be actually studying about the different saturation states of calcium carbonate, which are aragonite, calcite and magnesium calcite. So when we talk about this process, this actually happens through two different processes. One is directly through the temperature dependence of the seawater carbon dioxide chemistry, that is one. The second, it is indirectly related through air-sea exchange of CO2 and the subsequent changes to dissolved ionic carbons and total alkalinity ratio of the water. So these are all the two factors. We will be looking at that elaborately. So next we will look at the Revel factor, which is nothing but the buffering capacity of the ocean. So this is a very important factor, and the Revel factor is the ratio of fractional change in the seawater, that is the partial carbon dioxide pressure, to the fractional change in the total dissolved inorganic carbon after re-equilibration, that means at constant temperature, salinity and total alkalinity. So we know these things will change or affect the carbon dioxide concentration. So the Revel factor is given by this particular equation. The most important oceanic process that act as a carbon sink, because in the beginning we saw in the atmosphere, in the cryosphere, basically the cryosphere can actually act as a carbon sink. So that is how, what are the changes that is happening are given here. It is the dissolution or a chemical buffering of anthropogenic CO2. That is what is happening. So here, not all the 100% of the gaseous CO2 entering the ocean lead to an increase of CO2 concentration. So we had actually seen one particular process that phytoplankton can actually consume the carbon dioxide. So that means whatever the 100% of the CO2 that enters the ocean is not responsible for the ocean acidification, because part of that is being taken away by the phytoplanktons. So some of them are converted to carbonates and bicarbonate anions. So that is also taking place, because the bicarbonate getting converted to carbonate, the carbonate is consumed or converted to calcium carbonate. So the mollusk, shells and other things, coral reef, all consume this carbonate anion in the form of calcium carbonate, and they use it for their shell formation. So the re-equilibration of seawater results in the buffering of significant amount of carbon dioxide. So this Revel factor increases with the partial pressure of carbon dioxide. So the lower the Revel factor, the larger the buffering capacity of C factor. So this is what is the relation between these two. When the pH is high, that is basic, the Revel factor is, Revel effect is the greatest, causing much of the dissolved inorganic carbon to exist as bicarbonate and carbonate anion and not as CO2. So this is what is our simple understanding. So when the Revel factor effect is great, then we do not have free carbon dioxide. So as simple as that. And what is the application of this buffer factor? So basically this provides a convenient means to calculate the changes in the water chemistry under variety of experimental and natural conditions. So this helps us understand what is actually happening. The buffer factor can also be used to design experiments in which the variations in the carbon dioxide, pH and the calcium carbonate steady states can be minimized. The buffer factor may also be useful in the conjunction with model simulations such as global circulation models. And this factor provides information on relative sensitivities of different carbon parameters to future climate change. So these are all the applications. With that, we actually conclude, but if somebody is more interested in understanding the sea surface temperature and pH, they can continue watching this video. So the first process is the one we talked about. There were two processes we talked about. The first process is the control of chemical speciation of carbon dioxide in the dissolved seawater. So what actually happens in a closed system with a constant DIC, that is direct inorganic carbon, and total alkalinity, when the temperature increases from 20 to 25 degree, that is 5 degree increase, the dissociation of bicarbonate and water are the primary process producing hydrogen ion. So this is the process number one. A large portion of this hydrogen ions is consumed by borate, with most of the remaining H plus ion reacting with bicarbonate to form aqueous carbon dioxide, leaving a tiny portion of H plus ions in the seawater as H plus or H3O plus. So this is the next process that is happening. This tiny portion of H plus ion decreases the pH from 8.10 to 8.02 in many cases. So the extra carbonate from the dissociation of bicarbonate combined with the decrease of apparent solubility product with the temperature, that helps to increase the aragonite saturation state slightly from 3.16 to 3.25. So this is the change. The calcium carbonate is in the form of aragonite. So its saturation state can be increased when the pH, or in other words the hydrogen ion concentration, increases. The second one is which involves the air-sea gas exchange and the associated changes in the direct inorganic carbon and the total alkalinity ratio. So when the water temperature increases, the extra H plus ion formed from the dissociation of bicarbonate ion and water will now react with the most abundant carbonic species of the anion, which is the bicarbonate anion, driving it up to excess of aqueous CO2. So that is what actually happens. So this will dissociate it. When the temperature increases, the change of both atmospheric carbon dioxide and the solubility work together to create a tendency of seawater to degas CO2. That means they will just expel carbon dioxide to the atmosphere. This lowers the DIC to TA ratio. So this raises both pH and the aragonite saturation state. So similarly, at a low temperature, that is colder temperature, will enable the body of water to absorb more CO2, because at high temperature CO2 is expelled, at low temperature CO2 is absorbed. In order to maintain the equilibrium at the atmosphere, with the atmosphere, so it increases the DIC to TA ratio, and which results in the decrease of both pH and the aragonite saturation state. So at a higher temperature, aragonite saturation state increases, at low temperature the aragonite saturation state decreases. So if warming or cooling only impacted the seawater chemistry, let us say if we assume that way, then through speciation changes, surface pH would be 0.47 units higher near the poles than the equator. But on the contrary, the aragonite saturation state would be slightly lower near the poles than the equator, but this is not actually what is happening. If the air-sea gas exchange of CO2 were the only controlling factor, then the pH in the polar area would be 0.46 units lower than the tropical area, and the aragonite saturation state would be around 50% lower. So that means something increases and something decreases. So both are actually happening by the change of temperature. One process changes, or one process lowers the aragonite saturation between different places when we compare with the polar and the terrestrial region. In the other case, exactly the opposite thing happens. So these both effects nearly cancel the pH. So whereas they reinforce each other for aragonite saturation state. Due to this, the surface ocean pH does not show as strong a latitudinal gradient as aragonite saturation state. So this is what we can understand. That means the saturation temperature may not have major effect in this particular process.